Hi everyone, my name is Tal, and in this talk, we're going to together explore the question of whether we can take a high-level language like Python to fully represent a weather and climate simulation and still achieve state-of-the-art performance. So this work is a collaboration of the Scalable Parallel Computing Laboratory at ETH Zurich, the Swiss National Supercomputing Center, and the climate modeling team at the Elynn Institute for Artificial Intelligence. So first of all, weather and climate simulation almost needs no introduction. We're using climate simulation to understand which crops would yield most in the next season, who to evacuate in case of an extreme weather event, and even if it's going to rain at your wedding. In fact, numerical weather prediction is one of the oldest problems in high-performance computing, and it shows. So here is an excerpt of a code from a weather model. And as you can see, it's written in Fortran, as most weather models are. And that's what the atmospheric scientist has to work with. Right, so this code has a few issues in its contents rather than the syntax. We can see here. So for example, the domain size is fixed into the loop ranges. The loop order itself is fixed, and that might be something that you want to change from hardware to hardware. The schedule of the loops, for example, whether to run them as separate loops or fuse them together or recompute some of the results, that's also hard-coded. And even the data layout itself of the tensors is fixed into the code. Now, beyond the single node, where it comes much more complicated, is when we talk about communication. So all the tiling strategies, how we distribute the work across the nodes, that's all fixed and baked into the code itself, mixed with the computations of the model. So with the surge of recent hardware architectures that are coming in and more on the way, the burden of keeping up with all of those architectures and trying to optimize the code is on the atmospheric scientist. And that is unsustainable. So the question that we want to ask here is, what defines or what characterizes those computations, and how can we abstract away some of that so that we can make this work easier, more portable, and even more performant? And so for this work, we are using the grid tools abstraction for weather and climate simulations, which basically means that there are two kinds of computations. The first one is a horizontal stencil. So let's imagine here that those two horizontal dimensions are actually latitude and longitude, and the k dimension here are vertical planes above the Earth. And what we have in such computations is that we have horizontal dependencies, but only horizontal dependencies. So the entire computation here on every single slice can run in parallel. The other side of those computations is vertical solvers. So those are solvers that work on the individual planes, but with directionality. For example, going upwards or going downwards. And what we can see here is that the computations, they may not have kind of diagonal, so horizontal and vertical dependencies, but they do depend on the results of the previous computations. So this means that we can also parallelize that across the horizontal domain, but still we have those computations. Now, is this abstraction good enough to represent a full weather and climate model? Yes, this was used many times before for several weather models, and it turns out that you can encapsulate a lot of the computations that constitute, the heaviest computations in a simulation by these two abstractions. Now, in this work, we're also exploring a single model as our case study. This is the finite volume cubed sphere global forecast system, or FV3GFS for short. This is a global climate model developed by GFDL at NOAA. And it's not only used by NOAA, it's also used by other bodies as well to perform climate simulation, not only on Earth, but also on Mars. So very versatile, very kind of reusable dynamical core. And the way that this cubed sphere model works is that we divide a planet to 6 different faces. And that allows us to kind of evenly distribute the points across the whole globe, and also have this kind of trade-off that we can simply compute and very easily pack and transfer the information for boundary conditions to basically exchange between the faces of the planet. Now, the model itself has horizontal finite volume dynamics and vertical Lagrangian dynamics with remapping. And the baseline that we're going to compare with is this highly optimized production Fortran code that was, as mentioned before, baked or hard-coded for the multi-core x86 CPU architectures. But it is very well optimized for those, as we will see. Now, the project here as a whole is part of a very ambitious kind of attempt to completely rewrite the weather model in Python. So that is the goal of the Piz project. It is designed to have not a single line of Fortran in your code, but instead entirely run on Python and to run on a supercomputer while doing so. So you can call your code with Python-M here and really kind of compute the weather of tomorrow. Right, so the Dynamical core is a very complex piece of code. And the move to Python actually helps reduce that complexity somewhat. So the original code has 29,000 or almost 30,000 lines of Fortran. And then with this porting, we managed to reduce it by 40% to only 12,500 lines of code. But also, as you can see here, it is split across different modules that could also be reusable. And this is part of this architecture. We have Python and we have modules that represent sub-computations. And with that, we can actually take those parts of the Dynamical core and write unit tests for them, or write utilities for Halo Exchange. And so this is kind of the top level of how this project is written. Now, below that Python level, we have the grid tools-based abstraction of the two stencil types. And below even that, we have a code generator and orchestrator, which is based on the data-centric parallel programming framework. And that allows us to perform both local optimizations, but also transfer them into full program optimizations, as we shall see. So for certain things like Halo Exchange or other components, we can communicate between the generated code and the Python interpreter so that we have everything we need to run the entire model completely in Python, but also run it fast because we generate and compile code. And so this is the architecture of the overall approach. And we're going to go deeper into all of the individual parts and see how they combine together. So the first part that we want to touch is the Python version. As I mentioned, this is all nicely modular code. And the reason why we chose Python as a language is because it is clear that a lot of fields, and especially driven by this entire emergence of deep learning and other frameworks, that this is becoming the language for scientific computing. And in fact, Python is more than just a language. You can see packages here like NumPy, package management, a lot of domain-specific utilities, and even plotting tools that really help make this entire thing an ecosystem. And so if we want to use that ecosystem, here is how we did this with the Piz project, right? So here the Dynamical core is now rewritten as a set of modules, and they're all written in Python and have those unit tests that I mentioned before. And the contents of those are just object-oriented programming. We use methods and callers to compute this code. Now, as you can see here, this code is not very simple. All these numbers here on the top right, they indicate number of lines in the Python code. But in the end, this code is composed of stencils and for loops and conditions and sometimes data-dependent conditions. And all of that is something that we need to tackle and optimize in order to get this to run very performant. On the other hand, calling this entire Dynamical core is something that is actually very simple. We have a Python function called die_loop, and that has the time steps, and we just step. What this allows us, though, when we use Python, is to do really interesting things. We can load files using Python modules. We can validate the code with certain unit tests. We can even plot the results nicely and animate them on a map, because Python is just this ecosystem that has these modules for you, right? So here is an example of a Jupyter notebook that exists in this Pace repository. And you can see that we can run this code and interactively inspect the results. And this allows you to, change your model, for instance, right? So this increases productivity immensely. And so with this part, we actually have a proper object-oriented, nicely modular piece of code that represents the whole dynamical core. Now, the second part is how we go and take the abstraction that I mentioned before and implement the stencils with that. And so in order to do this, and even natively in Python, there is the GT4Py, or Grid Tools for Python framework, which essentially it's a domain-specific language designed specifically for those weather and climate applications. And instead of defining stencils in a very imperative format, the approach here is declarative, essentially saying what we need to compute and not exactly how. And it's designed, again, for three-dimensional stencils for computations of planets and those vertical solvers. But this also allows us to break free of some of those baked-in code elements. So if you remember this code from before, with all the hardware details that were fixed, this is what it looks like now. Only 3 lines inside that actually compute the stencil itself. So what do we see here? First of all, we see that the computational domain is completely abstracted. So we have fields, and they have dimensionality, but not size. So this is completely size agnostic. All the indices are relative, as is necessary for these two abstractions. We only need to look at relative indexes. The regions and how we want to communicate and what halos we need to compute and how much we need to allocate for each of those fields is completely automatic. And you can see here that with a simple with statement, we represent a horizontal computation. And lastly, and most importantly, is that all of the information about how to allocate, what memory layout you should use, and so on, is delegated to the backend, which here we use this Dace backend, which I'm going to get to in a bit. And this allows us basically to swap this string with anything else and then can just rewrite or regenerate a better or more specialized stencil. So this Dace backend that I mentioned is actually part of a bigger kind of mindset and framework and workflow, which is the data-centric parallel programming workflow. So just to give a bit of motivation, a lot of codes in domain sciences, not just atmospheric models, sometimes the algorithm looks something like this, right? So we have here a matrix multiplication with 3-dimensional for loop, or if you like, then writing it in Python, then the at operator does the same thing. But when we actually want to use the hardware to its full extent, what is happening is that we need to do a whole lot of specialization. So here on the right-hand side, what we can see is the example, the simplest code sample in the tensor core, to use tensor cores, which are units inside NVIDIA GPUs that are specialized for matrix multiplication. So the example in their SDK is 333 lines, but only a single line here actually does the computation. All the rest, they have to bring the data to the right place. So what we can conclude, and this is, of course, not just in this, is that the algorithm is really basically surrounded by all the data movement. And if I want to go into even more optimized implementations, like Cosma for matrix multiplication, not just an example, but really the state-of-the-art performance, we end up with thousands of lines, mostly related to data movement. And so not just for GPUs, but also for other architectures these days, or in the past few decades already, the high performance optimization has to do with data movement reduction more than anything. And so Dace was designed to essentially tackle that by having an intermediate representation that is only used for optimization of data movement. And so by mutating the data movement without modifying the original code, we can get high performance. The way that this works is, first of all, to acknowledge the existence of this performance engineer in the middle, right? We have domain scientists. They formulate problems in high-level or low-level languages, but scientifically formulating the problem without any optimizations. And then we convert this into a data-centric program through a set of passes and end up with this intermediate representation, which is called a stateful data flow multigraph, or SDFG for short. Now, this representation can be optimized and transformed without touching the original code, only by mutating data movement. And then this data flow can be mapped to a wide variety of hardware architectures, CPUs, GPUs, FPGAs, clusters thereof. And as opposed to standard compilers, this is not the end of the story. So here we promote kind of an open approach or workflow for optimization that can get you instrumentation via instrumentation and timing and performance models, getting results back to better inform you as a performance engineer to optimize your application further. And so there are different ways in which we can do that. We have graph transformations that are purely extensible, so you can write your own transformations if you want to. And if you don't know where you need to optimize something, we have visualizations of the local and the global data movement, so you can analyze and see where you might want to optimize something. And we even have tuning interfaces to work for local computations and also global tuning for an entire application. And so with that, we have all three components. And now we know that we need to combine them somehow together. So we know that the stencil implementations are written in GT4Pi from the space representation. And the backend is this stateful data flow multigraphs in Dace. So this provides us with everything we need for local optimizations, but then there is this final part where we actually need to take the entire application and orchestrate and globally optimize it. And this is what I'm going to talk about next. So here is the code that I've shown you before, the pure Python code. As I said, we now added GT4Pi here for the stencils. So each one of the stencil calls is written in this domain-specific language that is very declarative at high level. And on the other side, if we want to take basically the whole program, all 19,000 stencil calls, and compile them as one unit, all we need to do is add an @dace here at the top. And then once we call this function, it would gather all the functions and all the subroutines and compile them into one shared library. So this generates low-level code in C++ and C and CUDA and other languages to compile this into an object file that now, when we call the die-for loop here, instead of calling the Python code, we call the compiled fast code. But we still have all the nice capabilities of Python. We still have all the features we need. We can still plot it and run it in Jupyter Notebook, but now it runs fast. Now, what can we actually do with having this entire code written in one representation? Right, so it turns out there are many things we can do. So for local optimizations within each stencil, we can use both GT4Pi and Dace to get some nice optimizations going for each of those stencils. So for example, we can play with the computational layout and the data layout. So as you can see here, we even have this interactive visualization directly in an IDE, so Visual Studio Code, to show you whether you're being cache efficient with a certain computation. So really, the performance of a stencil depends on having a good combination of having the right order of loops, but also the right data layout so that you don't have too many cache misses, or that you can parallelize your code across a GPU and use coalesced access. So this now is fully controllable by our pipeline. Now there are more domain-specific optimizations that we can do directly in GT4Pi. So when we see those stencils, as I said, we know the halo regions, we know what we can recompute. So these are things that are directly now optimizable through this declarative, let's say DSL-based approach. So another example of such an optimization would be to take a branch that happens inside a stencil and turn it into a predication, which could be much faster in certain platforms. Now, where orchestration comes into play is in the optimizations that we can do between the stencils. So the global optimizations, now this becomes much more interesting, because when we transform something from, let's say, a CPU code to a GPU code, it's not just a matter of a directive on top of a loop. We can do fusion of different stencils. We can reschedule the computation of the entire dynamical core. For example, if I would like to run something on the CPU, we can take a subpart here and convert it into a single loop. So for example, as far as loop fusion is concerned, this is 7,500 lines that need to be rescheduled. And so this macro rescheduling becomes very effective in terms of performance. You also can control allocation, and allocation becomes very important when we deal with a full model, right? Because when you deal with a single stencil, your memory footprint is pretty low. But when you have all of these fields that you have to manage in 19,000 stencil calls, we really need to make sure we minimize the memory allocation and the memory footprint so that we can actually fit on a GPU, for example. So we do this via memory pooling and via static allocation and pre-allocation. And also we can tune the data layouts across different stencils by creating a coherent path between the different computations that makes sense. So we can output one layout and then reuse that layout as the input for the next stencil. Now, let's look at the graph representation of the stateful data flow, multi-graph representation of the entire model. As you can see, this blob here on the left-hand side of the slide is the entire thing. And it's pretty big, so we can zoom in maybe a little bit to see only one part of it. And what we can see is that it's still quite large. There are lots of computations here, lots of parallel computations. And let's zoom in even further on a single one of those computations. What we can see here is a single vertical solver, which is also containing control flow and data flow. And even as we go into the single, like individual computational units here, they also have a pretty long set of instructions to run, right? So this is a Python code here, and still there are a lot of mathematical operations. So working with this code manually as is would also not be a good approach. So what we can try to do here, and this is exactly what we do in the paper, is to create a semi-automatic pipeline to optimize this. And with this basic approach that we have of turning things into the declarative approach with a domain-specific language, and also using the framework, we can now automate some of that pipeline, but still keep it hybrid. So you can see here steps in the pipeline, and if it's colored in blue, then it means that the human works on this, and if it's colored in yellow, it is automatic. So the first step, just to save time, what we can do is we can set some initial heuristics. So for every individual computation, for every individual stencil, we select 2 representative stencils, and we tune all possible configurations of computation and data layout. So what we can see here is that the horizontal computations, this one ended up being the fastest approach. So intervals first, then operations, then K loop, then J and I, and the distribution into threads on a GPU. On vertical computations, we found that a different computational layout worked best. And for data layout, we really took this all the way into optimizing the data layout to its full extent to make sure every axis is aligned and everything is well coalesced with GPU memory access. And what you can see here is that we make use of post padding here on each of the dimensions, but also pre-padding to ensure that the first output element is always aligned. And so we can tune all of these knobs and change them further, but these are the initial heuristics that we selected. Now, we can use these heuristics, apply them to the entire application, so apply them to the entire dynamical core, and then we can auto-tune, and we can tune each module separately. So here we can see what we do. So we can take cutouts of individual subgraphs that run computations, and then we can run exhaustive tuning on them. We get some patterns that work best. Then we try to apply them all across the model. So then in this way, we don't have to automatically tune an entire weather application, but only small parts and see where they fit and where these optimizations can apply in different parts of the code. So if we didn't want to use this feature, which we call transfer tuning, because we transfer the knowledge of one optimization to the rest of the model, we would have had to run millions of such configurations, tens of millions of these configurations. But with transfer tuning, we reduced that to only 603. So all in all, what we can do is within a single day, so less than 3 hours on the Piz Daint supercomputer, we can tune each individual stencil, and then in the next 8.5 hours, we can go and reapply and see if it's faster on different parts of the model. So that's a step that you can just run once, and now you have your, let's say, fully tuned model. Now, another thing that we can do, since we're using the data-centric parallel programming framework, as I said, we can take results and we can use performance models to augment the results and then get back a certain, let's say, summary of how the model works. Because as we said, this is an optimization process, right? It is even an optimization cycle. So we might go through the cycle and try to understand where can we still improve the code, right? So here you can see that since stencils are mostly memory bound, we can construct a model, a performance model of basically taking the performance of the stencil and understanding what is the percent of the peak memory bandwidth. And then we can do this on each individual stencil that appears in the dynamical core. And then we can also rank them basically by their importance in the model. So this is something that we do now automatically, is that we take the runtime of the stencil relatively to the entire model. So you may have a very slow stencil that runs only once. That would not appear here, but something that runs many times and affects the performance and still runs suboptimally, this is what you would see in the ranking here. And so, yes, we can use this now. And as performance engineers, we can take these results and then go and manually inspect the suboptimal kernels, let's say. So for example here, and there are more examples in the paper, we took this Smagorinsky diffusion approximation. This is a very simple stencil. In fact, this is the entire code of the stencil, right? So it doesn't do anything that would justify it being 25% of peak. But as we go into the code and we look at what would happen, is that you can see here that there is a certain, let's say, domain scientific pattern that happens. And like you can see here, for example, power of 0.5. And this should be translated to a square root. However, in the way that we generate code by default, this would be a more expensive POW operator. And the same for those power of 2. So this could be implemented as a single multiplication. Right, so we see this. Then we say, okay, let's just write a simple transformation to fix this. And we write that pass, and then we just add it to the Python code that executes, and we apply it everywhere in the program. So this optimization and more can allow us to fine-tune the individual parts, and then continue with a cycle to go back and keep auto-tuning and see how we can optimize more. And in this fine-tuning approach, as you can see, for the Smagorinsky diffusion approximation, we just end up maximizing the memory bandwidth. And for many other stencils, we managed to improve. So as you can see, the cycle can continue and we can optimize even more. Now, we have all the pieces we need. Let's look at the actual performance. We have 2 systems that we evaluate. So we take the Piz Daint supercomputer, which has 1 GPU per node, the P100 NVIDIA GPU. And we have also results for the Joules Booster supercomputer, which has 4 A100 GPUs per node and a completely different CPU. So in this presentation or this video, we will be focusing on the Piz Daint supercomputer, but you're welcome to look at the paper for more results on the A100. And the domain size, the largest domain size we could fit on the GPU that works on the entire model was 192 squared grid per node for the horizontal domain and 80 vertical layers. And so before we even start to look at the performance results, we first want to analyze, let's say, what are our bounds for performance? So what can we expect in terms of the differences between the production optimized CPU and the GPU? So as we said, stencils are very much memory bound by definition. And so we benchmarked the CPU and the GPU of the Piz Daint node. And what you can see here is that the overall memory throughput here shows us that we can let's say, get up to 11.45 times performance speed up just by looking at the memory bounds. So this would be an expectation of kind of an upper bound of how much we can actually get with a GPU. And so the next step is to look at the actual representative computations, one form of vertical solver and another for a horizontal computation. So the representative vertical solver we chose was the Riemann solver, which is a semi-implicit solver for vertical velocity and pressure perturbation. And what we see here is that we try to scale the domains and see the performance both of the original Fortran production optimized implementation and the one that was obtained by Python. And what we can see here is that the results here for Fortran, they show the times here and also the scaling, which means how much slower was this time compared with this one. And as we can see, for a, let's say, relative size that goes up to 9 times the domain size, we see that the scaling is actually higher. So we get slower, we get almost 10 times slower, on a 9 times the domain size. And we looked at the performance counters, and the indications say that the CPU cache runs out. And we may estimate that even the data layout in the original Fortran implementation is not ideal to fully utilize the system. On the GT4 plus Dace side, what we can see is actually the inverse result. We see that the scaling is lower than what it should be. And by looking at the actual performance counters and implementation, what we can deduce is that we didn't have enough parallelism to fill up the entire GPU. But nevertheless, as we can see, the speed up goes from 6.6 to 8 times just for that vertical solver alone. Now, for horizontal stencil, we have finite volume transport. This is a module that actually is used in many different places within the model. Now, one key difference is the schedule change that I mentioned before. So basically, this finite volume transport runs within a context in the Fortran code that only operates at a single slice at a time. So it runs through multiple stencils. This thing, I think, includes more than 27 stencils that they all run on a single slice. And so that helps to fit on the L2 cache. And in the end, this yields much better performance. And as we can see on the GT4 Pi and Dace side, to run better on the GPU, we actually had to schedule this so that every individual stencil runs on the full 3-dimensional domain in order to, of course, utilize this GPU to the full extent. So here the effect on scaling with regard to the relative size is much more pronounced. We start with a 3.4 millisecond runtime, and we corroborate this cache utilization here by actually measuring the number of L3 misses. We can actually see that only 0.13% of the loads and stores are L3 misses, which means that for a very high part or very large part of this computation is actually done within the caches of the CPU. But as we increase the scaling, we can see that we run out of cache very quickly. And as we get to 9 times domain size, the code runs almost 31 times slower, right? And of course, we don't see this on the GPU side. In fact, here we see that the speed up actually gets closer and closer to this ideal memory bandwidth factor the more we enlarge the domain size. So what we see here is that this information can also inform us that maybe there is a better architecture somewhere between a CPU and the GPU that can keep the caches warm across kernels and also have a large enough cache size that accommodates for such domains in weather and climate simulations. All in all, the performance of the entire thing running on the Piz Daint supercomputer weakly scales nearly perfectly. And we can see that up to 2,400 nodes, we can maintain this between 3 and 4 times faster performance just by running this on the GPU. Mind you, this is the first time that the entire Dynamical core was run on a GPU. There have been attempts before to port some parts of FV3, but this is the first time that the whole thing runs on the GPU. And so with that, we managed to get 0.12 simulated years per day at 2.6 kilometer grid spacing. So, to summarize, within 6 weeks of work and 10 optimization revisions using the pipeline we defined, 4 performance engineers were able to optimize the production Fortran code to run on a P100 GPU at 4 times the performance, or A100 GPU with 8.5 times the performance. All of that without modifying the original model once. So to circle back to the question from the beginning, can we use Python to achieve state-of-the-art performance? The answer is yes, but with the right abstraction. So the entire code is completely open source. And there is even a Docker container where you can instantiate your weather model and just run it at will. And if you want to know more about the project or anything else, go to our website and find out. Thank you very much for listening.